Okay, let's unpack this. Imagine a world where the very air we breathe, the water we drink, and, well, the shifting seasons don't just influence life, but directly dictate the spread of dangerous diseases.
Yeah.
It might sound like, I don't know, a premise for a new sci-fi thriller, but
Mm-hmm.
for us, Homo sapiens, it's becoming an increasingly stark reality.
Mm-hmm.
Today, we're taking a deep dive into something profoundly important: how our changing climate is fundamentally reshaping the landscape of infectious diseases, transforming global health in profound and often unexpected ways.
What's truly fascinating here, I think, is just how intricately interwoven the climate system is with biological systems,
Huh?
our lives and the lives of the pathogens that affect us.
Absolutely.
For this deep dive, we're going to explore a comprehensive body of knowledge drawn directly from Chapter 125 of Harrison, which is, well, it's a foundational, almost encyclopedic text in the field of infectious diseases.
It really is the standard.
It is. And our mission here is to cut through the complexity and distill the intricate, often surprising connections between these long-term alterations in weather patterns and the epidemiology, the spread
Yeah.
of infections.
So think of this as your essential shortcut.
Exactly. Your shortcut to not just understanding, but truly mastering this critical nexus, equipping you with insights like, well, like an elite professional in the field.
Our goal for you, our dedicated learner, is to absolutely master this information. We'll start by tracing the science of climate change, from its fundamental mechanics, what's actually happening in our atmosphere,
Right, the basics.
to its specific observable impacts on temperature, precipitation, and those extreme weather events around the globe. Then, we'll seamlessly connect those dots directly to the spread of diseases carried by vectors.
Like mosquitoes and ticks.
Exactly, and those transmitted by water. We'll also zoom out a bit, look at even broader health challenges like large-scale population displacement and even conflict, all tied back to climate.
It's all connected.
So get ready for some genuine aha moments, because here's where it gets really interesting.
Mm-hmm.
So to truly grasp the profound impact of climate change on infectious diseases, we first need to build a solid foundation. We need to understand our changing climate itself.
That's step one.
When we talk about climate change, we're really not just referring to, a single unusually warm year or a particularly mild winter or even just a decade.
No, it's much bigger than that.
We're discussing something far more fundamental, a long-term systemic shift in our planet's entire operating conditions.
That's exactly it. The term climate change specifically means multi-decadal alterations across a whole spectrum of weather components.
Multi-decadal, so decade, century.
Right. These are shifts that unfold over decades and centuries in temperature, in precipitation patterns, in wind, in humidity levels, and, well, many other atmospheric factors. It's about a long-term fundamental recalibration of our planet's baseline, not just, temporary ups and downs.
And it's absolutely crucial, isn't it, to distinguish this from Earth's natural cycles? Because the planet has changed before.
Oh, absolutely. Our planet has a truly dynamic history. Over the past 2.5 million years, Earth has indeed experienced significant warming and cooling trends. It's cycled between vast glacial periods, those ice ages we learned about,
Right.
and warmer interglacial periods. During those immense stretches of time, average global temperatures swung dramatically, sometimes by as much as 4 to 7 degrees Celsius. Huge swings.
4 to 7 degrees. That's
Yeah.
massive on a global scale.
It is. For instance, if you look back at the last major glacial period, which finally ended around 12,000 years ago, global temperatures were, on average, a striking 5 degrees Celsius cooler than what we experienced in the mid-20th century.
5 degrees cooler.
We can see this vividly depicted in foundational climate data, often pulled from things like historical temperature proxies and ancient CO2 levels trapped in ice cores. That evidence is quite clear.
That historical context is absolutely vital because it throws into sharp relief just how unique our current situation really is.
It really does. The present climate period, the one we're in now, known as the Holocene, has been remarkably stable. I mean, for the vast majority of human civilization for millennia, really, temperatures have largely remained within a very narrow, consistent 2 to 3 degrees Celsius range.
Just 2 to 3 degrees of wiggle room for thousands of years.
Exactly. This unprecedented stability spanning thousands of years has been incredibly critical. It's precisely what allowed humanity to successfully populate and cultivate much of the Earth's landmass, enabling the development of agriculture, the rise of complex societies, and, well, everything we recognize as civilization. That consistent, predictable climate was the bedrock.
And here's the key distinction: the truly profound insight that sets our current climate trajectory apart. while Earth has always experienced natural shifts.
Hmm.
The current climate change is fundamentally different. Its primary cause.
Yeah.
Well, it's no longer really up for serious debate, is it?
No, the scientific consensus is overwhelming. It is overwhelmingly driven by human activities.
And its pace. That's the truly alarming part, isn't it?
That's the kicker. The current rate of warming on Earth is unprecedented in the last 50 million years. Just pause on that time frame, 50 million years. The speed at which this is happening is truly the game changer.
50 million years. That's hard to even comprehend.
Indeed. What's genuinely sobering is that a moderate projection, based on the best available scientific evidence, suggests that average global temperatures could warm an additional 1.4 to 3.1 degrees Celsius by 2100 compared to the late 20th century.
Just in this century.
Just in this century. And to put this into a startling perspective, a significant temperature increment, comparable to the shifts that unfolded over thousands of years during those vast glacial, interglacial periods of the past.
Right, those 4-7-degree swings took millennia.
Exactly. That same scale of change could now occur within the next mere 150 years. This rapid acceleration underscores the urgency. Despite being a relatively new scientific discipline in its modern form, climate science has provided an increasingly clear and robust picture of how the changing chemistry of our atmosphere has already influenced and will continue to influence the global climate. This isn't about guessing. It's about informed projections based on extensive data, sophisticated modeling, and a deep understanding of atmospheric physics.
So if this is happening so fast, what exactly is driving this unprecedented shift? What's the engine behind this rapid climate recalibration? It largely boils down to something we call greenhouse gases. Now, these aren't inherently bad, right? In fact, they're absolutely essential.
That's absolutely right. Greenhouse gases are a specific group of gases naturally present in Earth's atmosphere that possess a unique property. They absorb infrared radiation, heat.
Right.
By doing so, they effectively retain heat within the atmosphere. Think of them like a cozy blanket around the planet.
A natural blanket.
A natural blanket. Without these gases, Earth's average temperature would plummet to about 33 degrees Celsius colder than it is today. It would be largely uninhabitable, so we absolutely need some level of these gases.
But the problem arises when human activities start adding too much of these gases to the atmosphere, essentially making that blanket too thick, tipping that delicate balance.
Precisely.
Carbon dioxide, or CO2, is perhaps the most significant player here, particularly since the Industrial Revolution kicked off.
Yeah, CO2 gets most of the headlines, and for good reason.
Its primary sources are the combustion of fossil fuels, coal, oil, natural gas, and, unfortunately, widespread deforestation. Cutting down forests releases huge amounts of stored carbon.
And it's remarkable to note that as far back as the late 19th century, the Swedish scientist Svante Arrhenius actually predicted that increasing carbon dioxide in the atmosphere would lead to a rise in the planet's surface temperature.
He saw it coming over a century ago.
He did, incredibly prescient. Now, while water vapor is technically the most abundant and potent greenhouse gas,
I always wondered about that. Water vapor seems like a big one.
it is, but its relatively short atmospheric lifespan and its sensitivity to temperature mean it hasn't been a major factor in the recently observed warming trend. Its presence is largely dictated by temperature rather than driving the initial warming itself. It's more of an amplifier.
Ah, okay. So it responds to the warming caused by other gases.
Exactly. Other key gases include methane, which comes from fossil fuel production, livestock like cows, decomposition in landfills.
Right. Methane's quite potent, too.
Very potent, yes. Then there's nitrous oxide from fertilizers, fossil fuel combustion, biomass burning, livestock manure, and halocarbons, which are industrial chemicals used in refrigerants, electrical insulation, aluminum production.
So there's a whole cocktail of gases we're adding.
It is. And understanding how they work involves looking at Earth's energy balance.
Okay, let's get into the mechanics a bit. Earth's energy balance.
So our planet constantly receives incoming solar radiation from the sun. That's shortwave energy. A portion of this radiation, about a third, is immediately reflected back towards space by clouds, aerosols, tiny particles in the air, and the atmosphere itself.
Okay, so a third bounces off.
Right. The remainder, the other two-thirds, reaches Earth's surface, where it's absorbed and warms the land and oceans.
Got it. The planet heats up.
The crucial step occurs next. Earth, having absorbed this energy, re-emits it back into the atmosphere, but at longer infrared wavelengths, essentially, heat radiation.
So the energy changes form.
Exactly. And this is where greenhouse gases come into play. They are precisely tuned, chemically speaking, to absorb this outgoing infrared radiation. They trap much of that heat before it can escape into space.
Like the glass in a greenhouse.
That's the classic analogy. This change in wavelength from incoming solar to outgoing infrared and the subsequent absorption by greenhouse gases is fundamental to what we understand as the greenhouse effect. You can see it clearly laid out in Earth's energy budget models.
And to quantify this impact, scientists use a concept called radiative forcing. Now, this might sound a bit technical, but it's really important for understanding the scale of human impact, right?
It is. It's a core concept. Radiative forcing is essentially a measure of how much a particular factor, like a specific greenhouse gas, alters the balance of incoming and outgoing radiation to and from Earth's atmosphere.
So how much it tips the scales?
Precisely. And it's measured relative to a pre-industrial baseline, typically set at the year 1750, before we really started pumping these gases out in large quantities.
Okay.
What we see overwhelmingly is that greenhouse gases have a positive forcing, meaning on balance, they are increasing the amount of radiation, specifically that outgoing infrared radiation that is retained in Earth's atmosphere.
Yeah.
They're effectively adding more and more heat to the system over time.
So the blanket keeps getting thicker.
That's a good way to put it. And if you examine the data, particularly looking at the acceleration of radiative forcing from the major greenhouse gases between, say, 1850 and 2011, you see a dramatic upward curve. This isn't a subtle nudge. It's a powerful, accelerating influence on our planet's energy budget.
It's really taking off.
It is. This fundamental understanding of how greenhouse gases trap heat is the bedrock for comprehending all the cascading impacts we're seeing on our climate, and crucially for our discussion today, by extension, on global health and infectious diseases.
Okay, so we've laid the groundwork. We understand what climate change is, these long-term shifts, and how it works, the greenhouse effect, and radiative forcing. Now, let's talk about what it actually looks like in action. What are the observable impacts that are directly influencing the epidemiology of infectious diseases?
The real-world consequences.
When most people hear climate change, they think global warming. And while the global mean surface temperature has increased by about 0.85 degrees Celsius since 1880, that average number actually hides some crucial regional variations, doesn't it? Variations that are far more impactful, particularly for disease spread.
Indeed. That means global temperature increase, while significant, doesn't tell the whole story by any means. What's particularly relevant for infectious diseases are the localized and nuanced temperature changes.
Like where the warming is happening most.
Exactly. For instance, the Arctic, which you can think of as our planet's thermostat in some ways, has warmed at roughly twice the global average rate. It's not just warming, it's in a full-blown sprint compared to the rest of the planet.
Twice as fast in the Arctic. Wow.
We're also seeing winters warming faster than summers in many places. And perhaps most critically for vectors like mosquitoes and ticks, nighttime minimum temperatures are rising faster than daytime highs.
Okay, why are warmer nights so important?
Because insects are cold-blooded, warmer nights mean there's less of a break from the heat overnight. It extends their active hours, improves their survival rates, and literally expands their hunting grounds into new times of day and potentially new places that were previously too cold at night. Each of these specific nuances directly bears upon the incidence of infectious diseases, especially those transmitted by these cold-blooded vectors.
So it's not just hotter days, it's the lack of cool nights that really helps these vectors thrive.
That's a major factor, yes. And it's not just about average temperatures, but extremes. We've already seen a significant increase in extreme heat waves across the globe, and projections show they will become even more frequent and severe later this century.
And the consequences of these heat waves go way beyond just feeling uncomfortable.
Oh, far beyond. Beyond the direct morbidity and mortality in human populations, which are already substantial, causing heat stroke, exacerbating underlying conditions like heart and lung disease, these intense heat waves wilt crops. This contributes significantly to agricultural losses and destabilizes food systems.
Right.
Take the summer of 2010 heat wave in Russia. It was absolutely unprecedented in its severity. It ignited hundreds of forest fires that led to an estimated 56,000 deaths from air pollution alone, just staggering.
56,000 deaths just from the smoke and pollution.
On top of that, it tragically burned 300,000 acres of crops, including roughly a quarter of the nation's entire wheat fields that year.
A quarter of their wheat gone.
The hidden impact here, often overlooked, is the direct link to nutritional deficiencies. When heat waves destroy crops and disrupt food supplies, it leads to malnutrition, food insecurity, and serious economic hardship for farmers and communities.
And malnutrition weakens people, making them more susceptible to disease.
Precisely. Inadequate nutrition substantially underlies a portion of the global burden of many infectious diseases. It weakens immune systems and makes already vulnerable populations even more susceptible to illness. So a heat wave isn't just about heat stroke, it's about this cascading effect that primes communities for widespread disease outbreaks down the line.
Beyond temperature, climate change is profoundly shifting our planet's precipitation patterns. You mentioned the water cycle earlier.
Yes, the increased energy trapped in Earth's atmosphere by greenhouse gases directly influences the global water cycle. It supercharges it, essentially. This leads to more intense and erratic rainfall in some areas and prolonged, harsher droughts in others. It's like the water cycle is on steroids, becoming more extreme at both ends.
Wetter wets and drier dries.
That's a good summary. Since 1950, we've observed substantial increases in the heaviest precipitation events, those really extreme downpours, particularly in Europe and North America. While data is scarcer for other regions, it's likely that Southeast Asia and Southern South America have experienced similar increases in intense rainfall.
And the flip sides.
Conversely, other areas, most notably Southern Australia and the southwestern United States, have seen greater, more persistent drought conditions.
And there's a physical reason for this.
There is. The scientific basis is quite straightforward. A warmer atmosphere simply holds more water vapor. Specifically, it can hold about 6 to 7.5% more water for every degree Celsius of warming in the lower atmosphere.
So when it finally does rain, there's more water available to come down.
Exactly. It means that when it does rain, it's often a much heavier, more intense downpour. The crucial insight for our discussion is that both floods and droughts have been clearly and repeatedly associated with outbreaks of waterborne infectious diseases. It creates this double-edged sword of risk for human health.
Okay, so more extreme rainfall, more extreme drought, both bad for waterborne disease risk, and the oceans. You mentioned they're absorbing most of the heat.
Yes, the oceans, our planet's great heat sink, are playing a truly critical, albeit often unseen, role in all of this. They've absorbed a staggering 90% of the excess heat tracked by greenhouse gases since the 1960s. 90%.
90%, that's almost all of it.
And this isn't just a passive absorption. It has profound implications for extreme weather events like hurricanes, typhoons, and cyclones.
How does ocean heat affect hurricanes?
Ocean heat directly provides the energy, the fuel, for hurricanes. Consequently, warmer years tend to have greater hurricane activity and, more importantly, more intense hurricane activity.
So warmer oceans mean stronger storms.
Generally, yes. An analysis of satellite observations from 1983 to 2005 has already shown a discernible trend toward increasing severity of Atlantic hurricanes, even though their overall frequency has actually seen a slight decrease in some basins.
Fewer storms, but stronger ones.
That seems to be the trend in some areas. Looking ahead, modeling of future tropical cyclones suggests that their intensity could increase by another 2 to 11% by 2100. And perhaps even more worryingly, the average storm is projected to bring a staggering 20% more rainfall.
20% more rain from the average hurricane. That's a lot of flooding potential.
It is. What this means in real terms is potentially fewer, but much more powerful and much wetter, storms that unleash incredible devastation and, critically for our focus, create prime conditions for disease outbreaks in their aftermath through flooding and disruption of sanitation.
And then there's sea level rise. Another consequence of all this heat, particularly the ocean heat.
Absolutely. Rising sea levels are another critical, often slow-moving, but ultimately devastating consequence of a warming planet. Between 1901 and 2010, the global sea level rose by approximately 200 millimeters, or about 1.7 millimeters per year on average. That might sound small. Millimeter by millimeter.
Yeah, 1.7 millimeters doesn't sound like much in a year.
But here's the crucial insight. What's concerning is the acceleration. From 1993 to 2010, that rate nearly doubled to 3.2 millimeters annually.
It doubled in just a couple of decades.
Yes. Most of this rise has resulted from the thermal expansion of water as it warms, simply because water expands as it heats up. That's why the oceans absorbing so much heat is so significant for sea level.
So the water itself is getting bigger.
In effect, yes. Glacial ice melt is the second greatest factor, and its contribution is accelerating rapidly as ice sheets in Greenland and Antarctica melt faster and faster.
And the projections for the future?
Future projections are stark. By 2100, global sea level may rise by a full 0.8 to 2 meters. That's a huge range, but even the lower end is dramatic. The annual rate of rise could potentially reach 8 to 16 millimeters at the century's end.
8 to 16 millimeters per year. That's much faster.
Much faster. Ice melt from Greenland and Antarctica is projected to be the largest contributor to this accelerating rise. And the scary thing is, once those massive ice sheets really get going, destabilize past certain tipping points, there's potentially no turning back on human timescales.
And sea level rise isn't uniform across the globe, is it? That's another crucial nuance.
Correct. It varies regionally due to factors like ocean currents and gravitational effects. For example, the eastern seaboard of North America has experienced roughly double the global average rate of rise.
Double the rate on the East Coast. Why is that?
It's complex, related to changes in ocean circulation like the Gulf Stream slowing down, and the way the land itself responds to the melting of ancient ice sheets, a sort of geological rebound effect.
Okay. And to compound this, human settlement often leads to the subsidence of coastal areas.
Right, the land itself is sinking in many coastal cities due to groundwater extraction, building weight, and natural geological processes. This amplifies the effects of rising water. It's a real double whammy for coastal communities.
Sinking land, rising seas.
Exactly. This combination puts a truly massive number of people at risk. An estimated 300 million people living near coasts worldwide will be vulnerable to devastating flooding by 2050 due to the combined effects of subsidence, erosion, and sea level rise, and that's assuming no major levee upgrades are implemented.
300 million people potentially impacted by coastal flooding by mid-century.
It's a staggering number. We're talking about entire nations, low-lying island states, and vast populations in coastal megacities potentially displaced.
And it's not just about flooding, right? Rising seas affect freshwater, too.
A critical point. Beyond direct flooding, rising seas, along with extreme storms pushing salt water inland and the overuse of coastal aquifers, contribute significantly to the salinization and the intrusion of salt into coastal groundwater.
So salt water gets into the drinking water wells.
Precisely. This is a critical issue for water security, as about 1 billion people worldwide rely on these coastal aquifers for their potable water. It puts their access to clean drinking water directly in jeopardy. And when freshwater supplies are compromised, the risk of waterborne diseases like cholera or typhoid skyrockets.
Yeah, let's talk about some of the broader cascading effects of climate change that go beyond just direct impacts like heat waves and floods. One significant influence you mentioned is the El Niño Southern Oscillation, or ENSO. We hear about El Niño on the news, but its connection to our changing climate is profound, right?
Absolutely. ENS refers to these periodic, large-scale changes in water temperature in the eastern Pacific Ocean, occurring roughly every, say, 2 to 7 years, but averaging around 5. These cycles have dramatic, far-reaching effects on weather patterns around the globe, shaping everything from rainfall in Australia to hurricane seasons in the Atlantic.
And El Niño is the warm phase.
Right. The warmer-than-average water temperatures in the eastern Pacific define El Niño events, while cooler-than-average temperatures define the La Niña periods. Critically, there's accumulating evidence, there's still an area of active research, that climate change itself may be increasing both the frequency and the severity of these extreme El Niño events, amplifying their global impacts and making them even more disruptive.
Climate change might be making El Niño stronger and maybe more common.
That's what the evidence seems to suggest, yes. And these El Niño events directly drive alterations in weather worldwide, often leading to extremes, floods in some places, droughts in others. They are consistently associated with these extreme events, which in turn lead to higher rates of morbidity and mortality.
Can you give me an example?
Think back to Hurricane Mitch in 1998. It occurred during a strong La Niña, actually, but the principle of ENSO-linked extremes holds. Mitch was one of the most powerful hurricanes ever observed in the Atlantic. It unleashed an astounding 1 to 1.8 meters, that's 3 to 6 feet of rain over just 72 hours on parts of Honduras and Nicaragua.
3 to 6 feet of rain in 3 days. Unimaginable.
The devastation was immense. 11,000 people died and 2.7 million were displaced from their homes. And crucially, in the storm's immediate aftermath, there were devastating outbreaks of cholera, leptospirosis, and dengue fever. It's a stark, real-world example of how extreme weather, often intensified or modulated by these large climate patterns like ENSO, can trigger widespread disease and humanitarian crises.
And this leads us to what is often described as the final common outcome of all these climate change effects: human displacement and, tragically in some cases, conflict.
It's a grim reality. Imagine sea level rise inundating ancestral lands that people have lived on for generations. Extreme heat making entire regions physiologically uninhabitable for parts of the year. Heavy precipitation triggering catastrophic mudslides. Prolonged droughts turning once fertile ground to dust. And the salinization of water supplies rendering wells useless.
It paints a bleak picture.
All of these factors conspire to render regions, some inhabited by humans for millennia, simply uninhabitable. Think about the human stories behind this. For instance, the 8 million inhabitants of low-lying South Pacific islands are acutely vulnerable to sea level rise and could become climate change migrants, climate refugees, in the near future. This isn't abstract. These are real people facing profound existential choices about their homes and futures.
And this isn't just about environmental refugees moving peacefully. Climate change may also be a significant contributing factor, a threat multiplier for humanitarian crises and even conflicts.
Yes, that link is being increasingly studied and recognized. Scholars have argued, for example, that the severe 2011 drought in East Africa, which was almost certainly made more likely and more severe by climate change, may have directly incited the Somali famine. That crisis resulted in 1 million refugees and tragically high mortality rates. This wasn't just a natural disaster, it became a geopolitical one, intertwined with existing vulnerabilities and conflict.
That's a powerful connection.
Another clear illustration is the 2010 Russian heat wave we discussed earlier. Remember the massive crop failure?
Right, the wheat exports stopped.
Exactly. By forcing Russia to halt its critical grain exports, it caused a sharp spike in global grain prices. This, in turn, triggered food riots in developing nations across North Africa and the Middle East that were already struggling with poverty and political instability. Some argue it was one of the contributing sparks to the Arab Spring.
Wow, so a heat wave in Russia potentially fuels unrest thousands of miles away.
The underlying principle here is stark and undeniable. Without adequate nutrition, without consistent access to safe water, or without proper shelter, the basic necessities of life, the risks of infectious diseases, naturally, inevitably rise. These cascading effects underscore that climate change isn't just an environmental problem, it's a fundamental challenge to human health, global stability, and food security. It creates a fertile ground for infectious disease risks to multiply and spread in ways we haven't seen before, and professionals need to be acutely aware of these connections.
Okay, that's a comprehensive look at the climate side. Now that we've grasped the foundational science of climate change and its observable impacts, let's connect the dots directly to infectious diseases. How does this changing world translate to more or different disease threats?
Right, let's bridge that gap. While it might seem obvious that the incidence of most, if not all, infectious diseases depends heavily on climate factors like temperature and rainfall,
Sure, that makes intuitive sense.
it's crucial to remember that climate change is just one of many factors determining disease epidemiology. How diseases actually spread through populations in the real world.
Okay, so climate isn't the only thing that matters.
Not at all. That's a critical nuance. Even if climate change creates conditions that are theoretically favorable to the spread of certain infections, those diseases can often still be kept in check through robust public health interventions.
Like mosquito control or vaccines?
Exactly. Effective vector control programs like insecticide-treated bed nets or mosquito spraying, sanitation improvements, access to clean water, vaccination campaigns, timely antibiotic treatment, all these things play a huge role. This is why detecting the direct influence of climate change on emerging human diseases can be quite challenging sometimes because there are so many confounding factors and human interventions in play muddying the waters.
So it's hard to isolate the climate signal from everything else we're doing.
Precisely. This is where research with animal pathogens, animal diseases, provides invaluable insights. Because animal diseases are generally less monitored and less intervened upon than their human counterparts, they can often offer a clearer, sort of unfiltered signal of climate change's influence.
Ah, like a natural experiment.
In a way, yes. For example, studies have shown that the life cycle of tiny nematode parasites that infect caribou and musk oxen way up in the Arctic actually shortens as temperatures rise.
So the parasites reproduce faster in warmer conditions.
Exactly. And as the Arctic has warmed dramatically, researchers have observed higher nematode birdings in these animals, leading directly to increased rates of morbidity, sickness, and mortality. It's a direct, observable, and worrying link, showing how climate change alters the fundamental biology and impact of a disease in the wild.
That's a clear example.
Another compelling example comes from marine environments. The spread of the protozoan parasite Perkinsus marinus in oysters along the Atlantic coast. This parasite was historically limited by colder waters further north. But studies have clearly demonstrated how warming ocean temperatures have enabled its geographic range expansion, allowing it to infect oyster populations further poleward where it couldn't survive before.
So the warming water literally opened up new territory for the parasite.
That's right. These and other examples from animal studies make it abundantly clear how pronounced the influence of climate change on infectious diseases can be, even if it's harder to tease out in human populations sometimes. It sets the stage for what we might see, or perhaps are already seeing, in humans around the world.
Okay, let's turn our attention specifically to vector-borne diseases, those transmitted by insects and other arthropods like mosquitoes and ticks. The crucial point here, as you mentioned earlier, is that insects are cold-blooded, ectothermic creatures.
Absolutely. Their body temperature, their metabolism, their activity levels, everything is governed by the ambient temperature of their environment. Their geographic distribution, their very survival, is fundamentally dictated by it.
So as temperatures rise,
As temperatures rise, particularly those crucial nighttime minimum temperatures that provide less cold stress, insects are effectively freed to expand their ranges poleward towards the north and south poles and also up mountainsides into higher altitudes. These were areas previously too cold for them to survive year-round or reproduce effectively.
this opens up entirely new territories for disease transmission.
It does, impacting populations that may have no prior exposure or immunity to the diseases these vectors carry, making them particularly vulnerable.
But it's not just expansion everywhere, right? You mentioned heat can also be bad for them.
That's an important counterpoint. While new areas become climatically suitable, existing mosquito habitats, especially in already hot regions, may become unsuitable as a result of extreme heat stress exceeding their physiological tolerance. This could potentially shift disease burdens geographically rather than just expanding them everywhere. It's a complex, dynamic map of changing risk.
So some areas might see less risk eventually, while others see much more.
Potentially, yes. It's not a uniform increase globally. Water availability is another critical factor for insects, especially mosquitoes.
Right, they need water to breed.
Absolutely. Mosquitoes that transmit devastating diseases like malaria and dengue often breed in pools of water created by heavy downpours. More rain can mean more breeding sites.
But here's a fascinating paradox, a crucial nuance you touched on earlier. Breeding pools can also appear during periods of drought. How does that work?
It seems counterintuitive, but during droughts, rivers can recede significantly, leaving behind isolated, stagnant pools of water along the riverbanks or in depressions. These can create ideal breeding grounds for certain Anopheles mosquitoes, the ones that carry malaria. This has been observed, for example, in parts of the Amazon basin.
So too much rain is good for some breeding, but drought can also create specific kinds of breeding sites.
Exactly. This intensification of the water cycle, with both increased flooding and more severe droughts in different places or at different times, raises significant interest and concern regarding its potentially favorable impact on the spread of mosquito-borne diseases. It means public health officials have to prepare for increased risk under both extreme wet and extreme dry conditions, depending on the local vectors and environment.
Let's delve deeper into one of the most devastating vector-borne diseases globally, malaria. Temperature plays a critical, multifaceted role here, doesn't it?
Indeed. It's complex. Higher temperatures directly promote several factors crucial for malaria transmission. First, they can increase mosquito biting rates. Warmer mosquitoes are often more active and feed more frequently.
More bites, more chances to transmit.
Precisely. Second, higher temperatures shorten the parasite's reproductive cycle within the mosquito. This is called the extrinsic incubation period, or EIP. A shorter EIP means a mosquito becomes infectious faster after biting an infected person, increasing the transmission potential.
Faster turnaround time for the parasite.
Right. And third, warmer temperatures allow for the survival of the mosquito vectors of Plasmodium infection in locations previously too cold to sustain them year-round, particularly at higher altitudes or latitudes.
Like those highland areas you mentioned.
Exactly. Modeling experiments, for instance, have identified highland areas of East Africa and South America as perhaps most vulnerable to increased malarial incidence due to rising temperatures allowing mosquitoes to move uphill. An analysis of interannual malaria trends in Ecuador and Colombia, for example, documented a greater incidence at higher altitudes in warmer years compared to cooler years.
And people living in those highlands might not have immunity.
That's a major concern. Highland populations often lack the prior exposure and acquired immunity found in historically malaria-endemic lowland areas, making them more vulnerable to severe outbreaks and higher mortality rates when the disease arrives.
But here's a truly critical nuance you brought up, a deeper insight into the biological complexity. It's not a simple, linear relationship where hotter is always worse for malaria.
Correct. It's more complicated than that. While rising temperatures can expand the viable range where transmission is possible, malaria incidence isn't uniformly associated with every temperature increase. There's actually an optimal temperature range for transmission, typically somewhere between 16 degrees Celsius on the low end and maybe 34 degrees Celsius on the high end. Temperatures too cold or too hot can inhibit transmission.
Okay, so there's a sweet spot.
There is. And what's truly fascinating and often overlooked in simpler models is that rising temperatures can also have differential effects on the parasite's development during that external incubation period and on the mosquito's own feeding and egg-laying cycle, their gonotrophic cycle.
How so?
Well, if the temperature changes affect the timing of parasite development differently than they affect the timing of the mosquito's feeding and egg-laying, you can get an asynchrony, a mismatch between these two temperature-sensitive processes. And this mismatch has been shown in some studies to actually decrease the vectorial capacity of the mosquitoes, making them less efficient transmitters even if it's warmer.
So warmer isn't always better for the whole transmission cycle.
Not necessarily. It's a complex interplay, influenced by factors captured in epidemiological formulas, things like the vector biting rate, the probability of transmission per bite, the duration of the extrinsic incubation period, and the daily mosquito survival rate. It's a delicate biological dance that temperature can throw out of sync, sometimes in unexpected ways that might decrease transmission locally, even as the overall range expands. Professionals need to understand this non-linearity.
That's a really important layer of complexity. What about precipitation and malaria?
On the precipitation front, the abundance of Anopheles mosquitoes is generally strongly correlated with the availability of surface water pools for breeding puddles, ponds, slow-moving water edges. Biting rates, too, have been linked to soil moisture in some studies, which serves as a good surrogate indicator for the presence of nearby breeding pools.
So more standing water, generally more mosquitoes.
Generally, yes. Research in the East African highlands has documented that increased variance in rainfall over time, meaning more swings between wet and dry periods, has actually strengthened the association between precipitation patterns and disease incidence, making outbreaks potentially more erratic and harder to predict based on simple seasonal averages.
More variability makes it harder to plan.
It does. However, there's also a counterpoint. Extreme torrential rainfall, while initially creating breeding sites, can also paradoxically flush mosquito larvae and eggs from those very sites, potentially washing them away and temporarily reducing mosquito populations and transmission. So again, it's not always as simple as more rain equals more mosquitoes. Too much rain can sometimes be disruptive to them.
Fascinating. So thinking of future projections for malaria in a changing climate.
Climate models are becoming increasingly sophisticated. They can provide regional output that can assist national and local health authorities in planning. These models project future climate-suitable regions for malaria, accounting for the complex temperature and precipitation ranges necessary for transmission.
But you mentioned a crucial caveat earlier about these models.
Yes, it's vital to underscore this distinction. These climate suitability models typically do not account for the capacity of robust malaria control programs to halt or prevent the spread of the disease.
Hi.
Human intervention is a massive factor.
So the models show where the climate could allow malaria, not necessarily where it will be.
Exactly. But global reduction in malaria distribution over the past century makes it abundantly clear that even with climate change creating more suitable areas in some places, malaria occurs in far fewer places today precisely because of successful public health interventions like insecticide-treated bed nets, indoor residual spraying, rapid diagnostic tests, and effective antimalarial drugs.
Public health can override the climate signal to some extent.
To a significant extent, yes. So while climate modeling is an incredibly useful tool, especially for identifying potential future hotspots or areas where surveillance needs strengthening, particularly in regions with inadequate public health infrastructure, it's not a standalone predictor of actual disease occurrence.
What do the models generally suggest regionally?
Modeling studies in sub-Saharan Africa, for instance, suggest a complex picture. While some East African nations, particularly highland areas, may become more climatically suitable for malaria this century, some models suggest West African nations may actually become less suitable, as temperatures could largely exceed the optimal ranges for transmission, and the climate might become significantly drier in the Sahel region.
So shifts within Africa.
Potentially, yes. Conversely, higher temperatures and changes in precipitation could indeed allow malaria to move up the mountainsides of East African countries like Ethiopia or Kenya, and could potentially create favorable conditions in subtropical and temperate regions of the Americas, Europe, and Asia, where malaria was once endemic but was eliminated. This could challenge our current control strategies and require renewed vigilance even in areas considered malaria-free today.
Okay, shifting from malaria, let's turn our attention to another relentless mosquito-borne threat. Dengue fever, transmitted by different mosquitoes, Aedes primarily. Here, too, temperature doesn't just play a role, it practically writes the script for an outbreak, right?
Absolutely. Dengue transmission is highly sensitive to temperature. Higher temperatures, as clearly illustrated in studies on Aedes aegypti mosquito development, directly increase the rate of larval development and accelerate the emergence of adult mosquitoes from their aquatic stages, more mosquitoes emerging faster.
And the daily temperature range matters, too.
It does. A smaller daily temperature range, meaning less difference between the daytime high and nighttime low, just consistently warm, correlates with a higher transmission potential in some studies. Essentially, a more consistently warm environment keeps the mosquitoes active and the virus replicating efficiently.
Are there clear temperature thresholds for dengue, like with malaria?
Yes, there are. Temperatures below about 15 degrees C or above roughly 36 degrees C substantially reduce mosquito feeding behavior and survival, effectively shutting down transmission at those extremes.
Okay. And the virus replication inside the mosquito.
That's also very temperature dependent, just like with malaria's EIP. To give you a concrete example, in rhesus monkey models of dengue, the virus replication within the mosquito, the time it takes for the mosquito to become infectious, can occur in as little as 7 days at temperatures consistently above 32-35 degrees C. But it takes 12 or more days at a slightly cooler 30 degrees C, and replication doesn't reliably occur at all below about 26 degrees C.
So warmer temperatures dramatically speed up how quickly a mosquito can pass on the virus.
Dramatically. Research in New Caledonia reflecting these combined effects showed peak dengue transmission occurring around an average temperature of 32 degrees C. This temperature seems to perfectly optimize the shorter extrinsic incubation period, the higher mosquito feeding frequency, and the faster mosquito development cycle.
What about humidity? Does that matter for dengue mosquitoes?
Yes, peak relative humidity is also a strong predictor of dengue outbreaks in many locations. Aedes mosquitoes, like many insects, thrive in humid conditions, which helps prevent dehydration.
Yeah. And rainfall. You mentioned it was less consistent for dengue than malaria.
That's right. Interestingly, the association between dengue epidemics and precipitation is a bit less consistent in the scientific literature compared to malaria. This might be, and this reveals another important insight into vector ecology, because Aedes mosquitoes, particularly Aedes aegypti, often rely more on artificial domestic water storage containers for their breeding sites.
Things around the house.
Exactly. Things like buckets, discarded tires, unsealed water tanks, even flower pots and pet water bowls. They breed in small collections of water right where people live, rather than large natural pools created directly by rainfall necessarily.
So human behavior in storing water becomes really important.
Critically important. In fact, in some studies, increased access to a piped water supply has even been paradoxically linked to dengue epidemic.
Wait, piped water increased dengue?
Yeah, presumably because reliable piped water encourages people to store water in various containers around the home just in case the supply is intermittent, inadvertently creating more breeding sites for Aedes mosquitoes right within densely populated areas.
That's a fascinating unintended consequence.
It is. Nonetheless, several studies have still established rainfall as a predictor of the seasonal timing of dengue epidemics in many places, even if the direct link to the number of breeding sites isn't always straightforward. Rainfall might cue mosquito activity or influence humidity, for example.
Okay. Looking at the global picture for dengue.
The current distribution of dengue largely overlaps with the known geographic spread of Aedes mosquitoes, particularly Aedes aegypti and Aedes albopictus. However, it's worth noting, and this is crucial, that the presence of Aedes mosquitoes without dengue being endemic, constantly present, in large regions of North and South America and Africa, clearly illustrates the relevance of non-climate variables.
So just because the mosquito is there doesn't mean the disease is rampant.
Correct. Factors like effective public health interventions, vector control surveillance, human population density, patterns of human travel and movement, which introduce the virus, and the degree of urbanization all play critical roles in determining whether the mosquito presence actually translates into widespread disease transmission. These are crucial factors that determine the actual risk.
But The climate sets the stage.
The climate sets the stage, absolutely. And coupled climatic epidemiologic modeling, which tries to integrate both climate projections and disease dynamics, suggests potentially dramatic shifts in the relative vectorial capacity, the potential for transmission for dengue by the end of the century. This is particularly true in scenarios where little or no mitigation of greenhouse gas emissions occurs.
What kind of shifts?
These models predict significant changes in where dengue outbreaks are most likely to occur, generally pushing the boundaries of risk into new latitudes, both north and south, and potentially increasing the intensity or duration of transmission seasons in areas where it's already present. Mastering these predictive models is key for public health preparedness.
Beyond malaria and dengue, climate change may also favor the increased geographic spread of other arboviral diseases. Those are viral diseases transmitted by arthropods, like mosquitoes and ticks. Let's look at a few notable examples that have hit the headlines. Zika.
Yes, Zika virus disease. It moved into the Western Hemisphere from French Polynesia around 2013, spreading rapidly and causing major epidemics, particularly in Brazil in 2015-2016, famously linked to microcephaly in newborns. While air travel was obviously essential for its initial delivery to the Americas.
Oh, had to bring it over.
Exactly. But available evidence strongly suggests that the powerful 2015 El Niño event, which brought unusually warm and sometimes wet conditions to parts of South America, provided an optimal climate for the infection to truly take root, establish itself widely, and spread explosively once it arrived. And the primary vector there is, again, Aedes aegypti.
So El Niño created the perfect storm, climatically speaking, for Zika's spread.
It appears so, yes. Then there is chikungunya virus disease, another debilitating mosquito-borne illness causing severe joint pain. It emerged rather strikingly in Italy in 2007.
Italy. That seems far from its usual range.
It was. Chikungunya had previously been mostly a disease of African and Asian nations. Its appearance and transmission within Europe was a significant range expansion event, facilitated by the presence of the Aedes albopictus mosquito, the Asian tiger mosquito, which had already established itself there.
And climate change plays a role there, too.
Climate models now predict that, provided these competent vectors remain present or continue to spread, conditions will become increasingly suitable for chikungunya to gain a stronger foothold in Western Europe, especially perhaps southern France and other Mediterranean countries, in the first half of the 21st century.
What about West Nile virus? That's become a concern here in North America.
Yes, West Nile virus disease, transmitted primarily by Culex mosquitoes and amplified in bird populations. Outbreaks are generally expected to shift northward in North America throughout this century as the climate warms.
Where are the hotspots now, and where might they move?
Current hotspots include places like the California Central Valley, southwestern Arizona, southern Texas, and parts of Louisiana areas with compatible climates and abundant avian reservoirs for the virus. But by mid-century, climate models suggest areas like the upper Midwest and New England will become more climatically suited to sustained West Nile virus transmission. And by the end of the century, the area of highest climatic risk may shift even further north into southern Canada.
Moving steadily north.
Potentially. But ultimately, whether the disease truly moves northward and establishes itself will depend not just on the climate becoming suitable, but also on factors like the availability of susceptible bird reservoirs in those new areas, and importantly, the effectiveness of local mosquito control programs.
So again, climate enables, but other factors determine the reality.
Precisely.
Another significant vector-borne disease, particularly here in North America, is Lyme disease, carried by ticks.
Yes, Lyme disease is a major one. In recent decades, Ixodes scapularis, the black-legged tick, which is the primary vector for Lyme disease bacteria, Borrelia burgdorferi, as well as for related infections like anaplasmosis and babesiosis, particularly in the Northeast and Midwest U.S. Well, this tick has become established further north, into parts of Canada.
And that's linked to warming.
Directly attributable to warming temperatures, yes. The ticks simply couldn't survive the colder winters further north previously. Now they can. It's literally moving north as the climate allows.
And it's expected to keep moving.
Yes. With continued climate change, the range of this tick, and therefore the risk of Lyme disease, is expected to expand even further north and potentially westward. Lyme disease is already the most commonly reported vector-borne disease in North America, with estimates of maybe 30,000 reported cases per year, but likely many more undiagnosed.
What do the models predict for Lyme risk?
Predictive models, which have shown impressive, around 95% accuracy in mapping the current Exodes scapularis distribution based on climate variables, suggest a substantial expansion of suitable tick habitat deeper into Canada, particularly Quebec, and also potentially into states like Iowa and Arkansas by around 2080. This means significantly more people could be living in areas where they are at risk for these tick-transmitted diseases.
So for our listeners in those areas, that favorite hiking trail might soon become prime tick habitat, if it isn't already.
That's the unfortunate reality. Not exactly the kind of new neighbor you wish for, is it? It's a very clear illustration of how climate change is literally redrawing the map of disease risk right now.
But there's a nuance there too, right? Some places might get too hot.
Yes, that's worth noting. With a touch of regional nuance, some models suggest that areas currently suitable on the Gulf Coast may actually become less suitable for these specific ticks by the end of the century due to excessive non-viable heat during certain parts of the year. So again, it's about shifts in risk, not just universal expansion.
Okay, beyond insect and tick vectors, climate change profoundly impacts waterborne diseases. This comes back to the water cycle going wild, as you put it.
Exactly. Outbreaks of waterborne disease are strongly and consistently associated with heavy rainfall events. It's a direct cause and effect that we're seeing more and more clearly as these events become more frequent and intense.
How strong is that association?
It's quite robust. For example, a major review of 548 documented waterborne disease outbreaks in the United States found that a striking 56% more than half followed periods of above normal precipitation in the preceding weeks or months.
More than half linked to heavy rain, and we're seeing more heavy rain.
We are. Most of the United States, with the notable exception of the Southwest and Hawaii, has already experienced a measurable increase in the intensity of heavy downpours since the mid-20th century. The greatest intensification of the water cycle, in terms of these extreme precipitation events, has been observed in places like New England and Alaska.
And the future projections.
Looking to the future, climate models project that by 2100, these daily heavy precipitation events, the kind of downpour defined as an amount that now occurs only once every 20 years on average, will increase nationwide. Depending on the extent of future greenhouse gas emission reductions achieved globally, these currently rare events could become 2 to as much as 5 times more likely by the end of the century.
So those once-in-a-generation floods could become regular, almost yearly occurrences in some places.
That's the potential reality, yes. It means systems designed for historical rainfall patterns will be overwhelmed much more often.
So how does this heavy precipitation actually translate to disease? What's the pathway?
Most outbreaks occur through the contamination of drinking water supplies, both surface water like rivers and lakes, and groundwater from wells. Think about it. Massive rainfall overwhelms sewage systems, washes animal waste from fields, carries pollutants from streets and industrial sites, all into water sources.
Okay, direct contamination. Is there a time lag?
Yes, and it differs. Outbreaks related to surface water contamination generally emerge relatively quickly, often within about a month of the heavy precipitation event. But here's a crucial point for investigation. Disease outbreaks from groundwater contamination, which involves contaminated water slowly percolating down through the soil into aquifers and wells, tend to appear later, often 2 or more months after the rain event.
That delayed impact must make tracing the source even more challenging.
It does. It can obscure the link to the initial rainfall. A review of published reports consistently shows that bacterial pathogens like Vibrio species, including cholera, and Leptospora species, causing leptospirosis, often from animal urine, are among the pathogens most commonly involved in outbreaks following heavy precipitation events.
Now, a significant contributing factor to these waterborne disease outbreaks, especially in older cities, is an outdated infrastructure design. Combined sewer systems, or CSS. Tell us about those.
Right. CSS are a major vulnerability. Roughly 40 million people just in the United States and millions upon millions more worldwide still rely on these systems, which were common in the 19th and early 20th centuries. They combine stormwater runoff from streets and roofs and sanitary wastewater from homes and businesses in the same single pipe network, sending it all to a treatment facility.
What's the problem with combining them?
The critical flaw, the fundamental design problem, is that these systems were originally designed based on a 19th century climate, an era when heavy downpours were far less frequent and less intense than they are today. They simply weren't built to handle the volume of water we often see now during storms.
So they get overwhelmed.
Exactly. When heavy rain occurs, the volume of combined stormwater and sewage exceeds the system's capacity. To prevent sewage from backing up into homes and streets, these systems are designed with overflow outlets that discharge the excess, untreated mixture directly into nearby rivers, lakes, or coastal waters.
Untreated sewage going straight into waterways.
Yes, and the frequency of these combined sewer overflows, or CSOs, has been increasing in cities worldwide as heavy rainfall events become more common. These overflows are associated with discharges not just of raw sewage, but also heavy metals washed off streets, other chemical pollutants, and crucially for health, a wide variety of dangerous pathogens, bacteria, viruses, protozoa.
Have there been documented outbreaks linked to CSOs?
Absolutely. We've seen outbreaks of things like hepatitis A, dangerous strains of Escherichia coli like O157 Pathophysiology infection, and cryptosporidial disease, a nasty diarrheal illness caused by a parasite, in the U.S. directly linked to swimming in or consuming water contaminated by these sewer overflows. It highlights a major and often expensive infrastructure vulnerability in the face of a changing climate.
Beyond precipitation, washing things into water, rising temperatures themselves also have a direct impact on specific waterborne pathogens, especially certain bacteria, right?
Yes, particularly bacteria that naturally live in water, especially warmer waters. Warmer water temperatures directly favor the proliferation, the rapid growth of Vibrio species. This is a group of bacteria that includes Vibrio cholerae, the cause of cholera, but also other species like Vibrio vulnificus and Vibrio parahemolyticus, which can cause serious wound infections or gastroenteritis from contaminated seafood or water exposure.
So warmer water literally helps these bacteria multiply.
It does. This phenomenon has been clearly demonstrated in various parts of the world. For instance, in countries surrounding the Baltic Sea, which is warming particularly fast due to its high latitude and has relatively low salt content, conditions are becoming increasingly favorable for Vibrio blooms and associated infections. Similar observations linking warmer waters to Vibrio outbreaks or increased detection have been made in places like Chile, Israel, northwestern Spain, and the U.S. Pacific Northwest.
Is there a really striking example of this range expansion?
A stark, truly quantifiable example occurred back in 2004. There was a Vibrio parahemolyticus outbreak linked to eating raw Alaskan oysters.
Alaska. That seems really far north for Vibrio.
Exactly. This particular pathogen was previously unknown, undocumented, in Alaskan oysters. This single outbreak event effectively extended its known geographic range an astonishing 1,000 kilometers northward. It's a very clear, direct illustration of how warming waters are allowing pathogens to thrive and expand their territories into new, previously unaffected regions, posing new risks for seafood safety and recreation.
We discussed the El Niño Southern Oscillation earlier as a broader climate pattern, but it's worth revisiting its specific link to infectious disease outbreaks because its influence is so direct and profound in certain regions. It acts almost like a global amplifier for some epidemics, you said.
Absolutely. In the past, El Niño events served as a critical natural experiment, a model system, to investigate the potential for extreme weather-related infectious disease epidemics in a future warmer climate. Now, as we discussed, recent evidence indicates that climate change itself may be strengthening these El Niño events, potentially amplifying their already significant power to promote epidemic infections in certain susceptible regions.
And scientists have mapped these patterns.
Yes, over decades of observation, researchers have identified characteristic patterns of disease outbreaks that tend to occur in specific regions during and following El Niño or La Niña events. This mapping, understanding these teleconnections, helps us anticipate and potentially predict where the next disease hotspots might emerge based on the ENSO cycle phase. It's a key tool for forecasting used by professionals.
What's a disease with a particularly strong El Niño connection?
One particularly strong and well-studied connection is seen with Rift Valley fever, a viral disease affecting livestock and humans transmitted by mosquitoes. There's been a strong association documented between Rift Valley fever outbreaks and El Niño conditions in eastern and southern Africa going back as far as the 1950s.
Why El Niño specifically?
The El Niño conditions tend to favor the unusually widespread and persistent wet conditions, heavy rainfall, and flooding in parts of East Africa that are highly suitable for the hatching and proliferation of the specific Aedes and Culex mosquito species that act as vectors for the Rift Valley fever virus. It essentially creates massive temporary breeding grounds over large areas. Yes.
And this link is strong enough to predict outbreaks.
Remarkably, yes. Because of this robust association, predictive models based on monitoring sea surface temperatures in the Pacific and rainfall forecasts for East Africa have actually successfully predicted Rift Valley fever epidemics in humans and animals, sometimes weeks or even months in advance. For example, during the 2006-2007 El Niño season, developing outbreaks of Rift Valley fever were accurately predicted 2 to 6 weeks prior to their major occurrence in Somalia, Kenya, and Tanzania, allowing for some preemptive warnings and veterinary actions.
That predictive power is incredible. It shows how understanding these large-scale climate patterns can directly save lives and livelihoods.
It's a powerful testament to the strength of the climate-disease link when the connections are clear and the mechanisms understood. It's a prime example of climate science informing public and animal health action.
What about malaria and dengue in the context of ENSO?
The picture there is sometimes a bit more complex. While some studies have found inconsistent associations between El Niño and malaria incidents in various African countries, likely reflecting the complex interplay of climate with local factors like control programs and vector species, a stronger, more direct link has often been identified in South America.
Stronger in South America.
Yes. Research looking at long-term malaria incidents in Colombia between 1960 and 2006, for instance, revealed a chilling statistic we touched on. They estimated that a mere 1 degree Celsius temperature rise associated with El Niño conditions contributed to roughly a 20% increase in malaria incidents in susceptible areas. That's a significant jump directly linked to the ENSO temperature effect.
Wow. And dengue.
For dengue, El Niño years are frequently and consistently associated with an increased incidence globally in many tropical and subtropical regions. Research on dengue outbreaks in Thailand from 1996 to 2005, for example, showed that a significant portion, somewhere between 15 to 22% of the month-to-month variance in dengue disease incidence, was directly attributable to the influence of the El Niño cycle.
So El Niño explains a good chunk of the ups and downs in dengue there.
It does. Similarly, looking across South America, data on dengue outbreaks between 1995 and 2010 consistently showed an increased incidence during the strong El Niño events of 1997, 1998, and again in 2006-2007. It reinforces the conclusion that these large-scale climatic phenomena are powerful, overarching drivers of epidemic risk for key diseases that professionals in the field must constantly monitor and factor into their planning.
Okay, we've covered a lot on the direct links between climate change and specific infectious diseases vectors, waterborne pathogens, the influence of ENSO. But beyond the direct transmission of pathogens, climate change has much broader, more fundamental health consequences that we, as informed citizens and professionals, really need to deeply acknowledge.
That's a crucial point to transition to, a really essential insight for the bigger picture. While the implications for infectious diseases that we've just discussed are indeed far-reaching and complex, it's important to realize that the greatest overall disease burdens resulting from climate change in the coming decades may not be primarily due to infections themselves.
So other health impacts might actually be larger.
Quite possibly, yes. It's about the foundations collapsing. Climate change disrupts the very foundations of health and well-being for huge numbers of people. It directly undermines fundamental access to safe drinking water, as we saw with salinization and contamination, and access to sufficient nutritious food through impacts on agriculture like droughts and heat waves.
And this sets back other health progress.
Absolutely. In doing so, it has the potential to unravel decades of hard-won progress against major existing global health problems, such as malnutrition and child stunting. And as we've repeatedly stressed, malnutrition inherently increases vulnerability to all infectious diseases, creating a vicious cycle.
And then there's the conflict link again.
Yes. Furthermore, the increasing scarcity of vital resources like fresh water and arable land, combined with general climate instability pushing people to migrate, are becoming more and more associated with humanitarian crises and, yes, potentially conflict. We mentioned the arguments linking severe droughts made more likely and intense by climate change as a contributing factor to the Arab Spring revolutions and the devastating Syrian civil war. These events led to massive displacement, breakdown of health systems, and immense human suffering.
It's a threat multiplier.
Exactly. It takes existing vulnerabilities and stresses and makes them worse. This again underscores that fundamental point. Without adequate nutrition, without safe water, or without proper shelter and stability, infectious disease risks inherently rise within displaced, stressed, or vulnerable populations. Climate change creates a fertile ground for illness and instability to take root and spread.
So given these immense and interconnected challenges affecting everything from malaria patterns to global stability, what's the public health response? How do we, as a global society, confront this?
It really boils down to two main strategies, right? Mitigation and adaptation.
That's the framework, yes. Mitigation and adaptation are the two pillars of the response. Mitigation is essentially primary prevention. It involves tackling the root cause of the problem directly.
Cutting the emissions.
That's correct. Mitigation is about drastically reducing greenhouse gas emissions into the atmosphere, trying to limit the amount of future climate change we lock in. Now, while there isn't one universally agreed upon safe threshold for greenhouse gas emissions below which there are no impacts, we're probably past that point anyway.
We are likely past the point of no impact, yes. But national governments from major industrialized countries have, through international agreements like the Paris Agreement, agreed to a collective warming target of aiming to keep global warming well below 2 degrees Celsius, above pre-industrial levels, and pursuing efforts to limit it to 1.5 degrees Celsius by 2050 or soon after.
Ambitious goals.
Very ambitious. Achieving even the 2-degree goal would require drastically reducing global greenhouse gas emissions by an estimated 40 to 70% below 2010 levels by mid-century, a monumental societal and technological transformation. The 2016 Paris Agreement provides the global framework for this, including provisions for things like establishing a global carbon market, technology transfer, and climate finance, all designed to speed up these necessary reductions. It's a blueprint, albeit one facing implementation challenges.
And crucially, these mitigation efforts aren't just about saving the planet in some abstract future. They offer direct, immediate health co-benefits right now, don't they?
They absolutely do, and this is a critical point for public health advocacy. For example, reducing the combustion of fossil fuels, burning less coal, oil, and natural gas for energy and transport, leads directly and immediately to better local air quality.
Less smog, less particulate matter.
Exactly. Better air quality, in turn, results in a lower incidence and severity of respiratory infections, from things like bronchitis and pneumonia to exacerbations of asthma and COPD. It also reduces cardiovascular disease risk.
What about things like cook stoves?
That's another fantastic example. Promoting clean cook stoves in developing nations, replacing traditional biomass burning stoves, simultaneously mitigates climate change by reducing emissions of black carbon soot, which is a potent short-term warming agent, and it drastically reduces indoor air pollution. Indoor air pollution currently kills roughly 4 million people a year, mostly women and children, from respiratory diseases. It's a true win-win scenario where climate action directly translates to massive, immediate improvements in public health.
And we've even seen this link highlighted during the recent COVID-19 pandemic.
Yes, that was quite striking. Emerging evidence during the pandemic showed that long-term exposure to air pollution, the kind reduced by climate mitigation efforts, may contribute significantly to a higher risk of severe illness and mortality from COVID-19. So, mitigation efforts that clean our air have very tangible, immediate health returns that benefit everyone right now, not just future generations. It strengthens the case for urgent action.
Okay, so mitigation tackles the source. On the other side of the coin, we have adaptation. This could be thought of as secondary prevention, right? Dealing with the impacts we can no longer avoid.
That's a good way to frame it. Adaptation is about learning to live with and minimize the harms associated with the climate impacts that are already happening or are now unavoidable, effectively baked into the system due to past and present emissions. This includes dealing with things like sea level rise, more frequent and intense heat waves, floods, droughts, and devastating wildfires. It's about building resilience in our communities and health systems.
What are the challenges with adaptation?
Well, the efficacy of adaptation, while absolutely necessary, is constrained by some inherent challenges. Perhaps the biggest is the difficulty in predicting the precise location, duration, and severity of future extreme weather events, or the exact extent and timing of sea level rise-related flooding at a very local level.
So it's hard to know exactly what to prepare for, where, and when.
Exactly. While we can prepare for general trends, more heat waves, generally higher flood risk in coastal areas, tailoring highly specific, cost-effective adaptation measures for unpredictable localized events remains a significant hurdle. Imagine trying to decide exactly how high to build a city's seawall or where to place cooling centers. We don't know precisely how high the water will get in the next specific storm surge or exactly which neighborhood will be hottest during the next heat wave.
So uncertainty makes adaptation planning tricky.
It does. So while things like improved early warning systems for storms and heat waves, developing drought-resistant crops, strengthening public health surveillance for climate-sensitive diseases, and building climate-resilient infrastructure are all vital adaptation measures, they can only do so much, especially if the underlying climate change continues unabated. Ultimately, both mitigation and adaptation are essential, interlocking strategies for protecting public health in a changing climate. One won't work effectively in the long run without the other. Adaptation buys us time and reduces harm now, but mitigation is needed to prevent the problem from becoming completely unmanageable.
If we connect all this back to the bigger picture then,
Yeah.
wow, we've seen how meticulously science maps the profound, intricate connections between our planet's changing climate and the delicate dance of infectious diseases.
It's truly a web of connections, from the foundational chemistry of greenhouse gases trapping heat to the specific vulnerabilities of malaria transmission in a warmer highland world, or the sudden surge of waterborne illnesses after extreme rainfall events. The story is one of deeply interconnected systems.
And the influence of climate change extends far beyond just the diseases themselves, doesn't it? Touching upon global stability, food security, water access, human displacement, creating challenges that ripple across societies in complex ways.
Absolutely. It's a threat multiplier that affects nearly every aspect of human health and well-being, directly or indirectly.
So what does this all mean for you, the discerning listener, tuning into this deep dive? Understanding this isn't just about absorbing facts, is it?
Not at all. It's about seeing the world through a powerful new lens, equipped with the kind of integrated knowledge that elite professionals in public health, medicine, ecology, and policy rely on every single day. It's about recognizing the systemic nature of these challenges.
And recognizing the critical importance of both those global mitigation efforts, trying to stop the problem at its source, and the local adaptation strategies needed to build resilience for what's already coming down the pike.
Exactly. This isn't abstract science happening somewhere else. It's about the air we breathe, the water we drink, the food we eat, and the health and stability of our own communities, wherever we live. It affects everyone.
Which really raises an important final question, something perhaps for you, the listener, to ponder as we wrap up. Given the accelerating pace of climate change that we've discussed, and its complex, often nonlinear impacts on disease transmission, vector ranges, and human vulnerability, what new, perhaps presently unknown or underestimated pathogens or disease vectors might emerge from previously unsuitable regions in the coming decades?
That's the unsettling question, isn't it? What surprises are potentially lurking as ecosystems shift? It could challenge our preparedness, our surveillance systems, our medical countermeasures in entirely unprecedented ways. We're undeniably on the cusp of a new epidemiological era shaped by climate change. And understanding these drivers, mastering this information, is the first absolutely crucial step in navigating it.